because for digital gates we have to use only 0 and 1. So we are using this logic gates. Like if we have to produce electricity from solar energy, so what we need a solar panel. Same way, for using this digital signals, we need this logic gate. Okay. So logic gates are the circuit designed to produce the basic logic functions such as AND, OR, etc. Okay. So here we are using basic types of logic gates, which are the AND gate, OR gate, and NOT gate. We have also included the truth table and Boolean expression using plus is denoted for OR, dot is denoted for and this minus is denoted for not. Okay. So here, don't get confused. Like because and is also called as plus, so it doesn't mean like and is plus. Here it is the opposite. So we here plus sign is used for or. Okay. And dot here means multiplication, logical multiplication. That so that is used for and this not is used for this not gate. So first topic of this logical gates is a buffer. So what is a buffer? A buffer do not affect the logical state of a digital signal. That is, if a logic 1 input results in a logic 1 output, whereas logic 0 input results in a logic 0 output. So here, the whatever input we are giving as a logic 1 or logic 0, so this buffer, it does not affect the output of the logic signal. It only increases the strength of the signal. So buffer, if you use it as a term, so it like enhances the signal. Okay, buffer, it means it increases the signal. So like if I am sending a signal from my side to your side, and if I am sending through wireless, okay, it is sent from one antenna to other. So like I am sending through this wireless, so this air, it creates some resistance, or like some fog is there or some rain is there. So what happens, this fog and rain, it absorbs some signal, so our signal becomes weak. So when it is reaching to your side, the signal is becoming weak. So if I am like sending a message in logic 1, so what is happening, logic 1, if you are taking it as 5 volt, so when it is coming to your side, it is either becoming like 4 volt or 3 volt. So what does this buffer do? It says that it is approximately like one in the logic symbol. Okay. So what it does, it makes that 3 volt to 5 volt, or it makes that 4 volt to 5 volt. So a buffer, it acts as an enhancer of the signal, or it increases the signal. Okay. So what is the Boolean expression for the output? So here what we are doing, we are taking output as y and the input as x. So our Boolean expression will be y equal to x. Okay. So this is a symbol for buffer, and this is the Boolean symbol. This is mostly not required, but as it was given in the book, I have put it here. So this is a Boolean symbol. So this logical, we also call it as Boolean algebra. So here they have given this Boolean symbol. So this is the truth table. So x is the input and y is the output. So if we are giving input as 0, we are getting output as 0. And if we are giving input as 1, I'm getting a output y also as 1. So I will show this through logism. So the people who are new, they can download Logism through the links I have sent. So if you have a laptop, then you can download Logism. If you don't have a laptop, then you please go and download this Logic Simulator and try to do all the circuits after the class. Okay. So in Logism, here are the different types of gates you can get. So uh, we are starting about buffer. So we will click on this buffer, and we will put it here. Okay. So here we got a buffer. Then we will put an input. So this symbol is the input and this symbol is the output. Okay, so we will put the input and output in our design area. So this is the design area. It is called as canvas. So here, this is the selector. Okay, to move any input or output, we will use a selector to move the gate or to delete the gate. We will select the selector. So here we can say that here in the input it is written as east. What is this east? It means that wire is coming out from here, so it is going in the east direction. If we just put it in the west side, so this wire will go in the west side. Okay. This wire is coming out in the west side. And if we do it as north, then it is going like up. So we have to put the wire in a such a way that it will go directly into the gate. So it should be in the east side. And same way with output. Here the wire is coming from here. So it means it is facing in the west side. Okay. So how we will connect the wire? We will simply click on here. You can see a green bubble will come. It means we have to connect the wire. So we will connect the wire. So here our connection is over. Then we will name the input and output. To name the input and output, we will use this edit text button. So we will click on here and we will put a X as input and we will put a Y as output. Okay. So we have completed the circuit of input and output, and we will check the truth table. For our input 0, we are getting an output of 0, and for input 1, we are getting an output of 1. Okay. So if we click on this circuit, you won't get anything because now this text is selected. That's why to click on the input and output, we have to select this button. So we will click on this button and we see that if X is 0, our Y is also 0. And if we click it over here, if our, so this light green, it means that it is not working. Okay. And when we make it as 1, it means that this is working. It has become light green. It means it is high or it is 1. Okay. So if we give input as 1, then we are getting an output of 1. Here we can also analyze the circuit. We will go to project. We will go to analyze circuit. So here we can see input. Our input is X. The output is Y. And that this is the truth table. For 0 we are getting a 0 and for 1 we are getting a 1. And in the expression we will get for output Y, our expression is equal to X. So this is the expression we are getting. And this is all about logisim. Any doubt in buffer? What is a buffer? So we will switch to next topic, NOT gate. Anyone can tell what is a NOT gate? What is a
In-
NOT gate?
Inverter.
Why we are calling it as inverter?
because it invert the signal from 1 to 0 or 0 to 1.
Yes, good. So this NOT gate, we also call it as inverter. Why we are calling it as inverter? Because if we give a 1, it will produce a 0. Okay. So 1 means high signal. So if we are giving a high signal, then it will give a low signal if you pass through a NOT gate. And if you give a low signal, then it will produce a high signal. It's just the opposite. So that's why it's called inverter. What is inverter means? Like inverter means it is inverting it. So that's why it's called an inverter. So inverter is also like acting like a buffer. So it provides extra currents. Like uh, if some note comes, then you also write this line. So inverter also provides extra current drive like buffer are used in interfacing application. So what is interfacing application? Interfacing application means connecting two devices. Like if you have a Bluetooth speaker or Bluetooth this headphone, what you do, you connect with your mobile, like pairing, okay? Or you have a mobile, you have to connect it to your laptop. So what you are doing, you are connecting a USB cable from your mobile to your computer. So you are connecting two devices. So that connecting two devices or this pairing, this is called as interfacing. Okay, so it is used for interfacing applications where they provide the means to regularize the logic levels. Same way in buffer, if the signal becomes lower than 5 volt, so it will make it to 5 volt. Okay, so it is acting like a buffer, but it is inverting the signal. So this is the expression. If our output is y and the input is x, so we have put a x naught. It means it is like x is, if our x is 1, then this x bar, it means it is the opposite. Like it is the not expression for x. Okay, so it is denoted by x bar. So this is the symbol for our NOT gate. This is the Boolean symbol. So what is the difference between the buffer and this NOT gate? Here we have provided a bubble. Okay. So this bubble means it is an opposite gate. So wherever there is a bubble, it means it is a NOT gate. Okay. So in Boolean single also we have put a bubble. So here is the truth table for NOT gate. So if we give an input of 0, then we are getting an output of 1. And if we are giving an input of 1, then the output we will get it as 0. Okay. This we will do in the logisim. So I will just replace this buffer with a NOT gate. So yeah, if we are giving an input of 0, then we are getting an output of 1. And if we are giving an input of 1, then we are getting an output of 0. So we will analyze the circuit. So here is the input x, output y, and here is the truth table. For 0 we are getting as 1, and for 1 we are getting it as 0. And this is the expression. Okay, for y it is x bar, or this it is a representation of x naught. So we have completed this NOT gate. Next, we will do the AND gate. So AND gate is not doing addition. Just remember this, AND is not addition. Okay. Like if a teacher calls you for a project, okay, he will say that all the students have to come, then only I will give marks. It means like, and everyone should come. So a first person, second person, three people are there, all should come, 1 2 3, so all should come, then only I will give marks. So that is a type of and expression, like all should come, then only she will give marks. And if like teacher is saying that anyone will come and I will give the marks, so that is or. So either person 1 should come, or person 2 should come, or person 3 should come, or all 3 should come, then they can get the marks. So that is an or gate. Okay. But in AND gate, everyone should come, then only we will get marks. If one is absent, then we won't get any marks. So that is AND gate. So AND gate operates on logical multiplication rules. So here this is the expression for AND gate. It is A dot B, or A multiplied by B. Okay. So multiplication we are denoting by dot. So this is our input A, B, and the output is Y. And this is the Boolean symbol for this AND gate. And here is a truth table. So our input is A and B. So in Boolean, when we were studying data representation, what we saw that how many types of combinations we can make through two inputs. It is 0 0 0 1 1 0 and 1 1. Okay. So input A and B is there. So what is output Y? It is the multiplication of A and B. So if we multiply 0 and 0, so we will get a 0. If we multiply 0 and a 1, then also we will get a 0. if we multiply 1 and 0, then also we will get a 0. But if we multiply 1 into 1, then we will get a 1. Okay. So this truth table is defined here in this notes. So here what we can see, that we are only getting 1 if the all the inputs are 1. So here we have written it in our definition. AND gate will only produce a logic 1 output when all the inputs are simultaneously at logic 1. Okay. Any other combinations as logic 0, then the output will also be 0. So if any one input is 0, then our output is 0. And if all the inputs are 1, then only our output will be 1. Okay. So this is the definition for AND gate. You write all these things. You write the expression, you draw this symbol. You draw this Boolean symbol is not that necessary, but this symbol and this truth table is the most important. Even if you don't write, just draw the symbol and draw this truth table. It is more important. So we will make this AND gate over here in the logism. So we will put two inputs A and B. We will put a AND gate. So by default, this AND gate is 5 inputs. So we have to scroll up and make it to 2. Here data bits is 1. So this is correct. And this is small size. We will make it as wide. This is medium size. We will make it wide. And we will put one output over here. Connect this inputs. And connect this output. We will name the input and output. This as A, this as B, and this as Y. So we will see the logic. If we have 0, 0, then we will get 0. If we have 0, 1, then we will get a 0. If we have 1, 0, then also we will get a 0. Only with input as 1, 1, we will get a 1. So we will check this. We will click on hand button for 0, 0. The output we are getting at as 0. For 0, 1, also we are getting a 0 because this is multiplying these two signals. For 1, 0 also it is, we will get a 0. And for 1, 1, we are getting a 1. Okay. So we will just analyze circuit. So here we can see this is the truth table. And if we go to expression, we will see the output Y. I don't know why it's giving X. It is A into B. Here you can't see the dot, but dot is not here, but it will be A into B. Okay, so this is the expression. Any doubt in AND gate?
No, ma'am.
So next I will do OR gate. As I told you, like if your teacher says if any one person will come, then she will give marks. So that is OR gate. Either one person should go or 2% should go or 3% should go. So they will get marks. So this is OR gate. So this gate performs the logical operation of addition. Sorry, here it will be addition. So OR gate will produce a logic. So we will see the expression. So what is the expression? Here y equal to a plus b. So this is logical addition and this is not binary addition. I am reminding you binary addition is different and logical addition is different. Okay. So we have input A and B and this is the symbol. Here the input it becomes little bit curved and this output will also become little bit curved for this OR gate. And this is the Boolean symbol. And this is the truth table. So we will add this input A plus B. So if we add 0 plus 0, then we will get a 0. If we add this 0 plus 1, then we will get a 1. If we add 1 plus 0, then also we will get a 1. And 1 plus 1, if we add, then also we will get a 1. Okay. So for Boolean addition, if we add 1 plus 1, then we will get 1, 0. But here we are doing logical addition. Okay. So 1 plus 1 also becomes as 1. So don't confuse this with Boolean expression. Uh, so by seeing the truth table, what we can say, if either of the input is 1, then we are getting a 1, and if we are only getting 0 if all the inputs are 0. So this is only what is defined here. OR gate will produce logic 1 output whenever any one or more inputs are logic 1. And putting this in another way, OR gate will produce a logic 0 output whenever all the inputs are simultaneously at logic 0. Okay. So this is the definition for OR gate. If it comes in exam, you should write the truth table, and seeing the truth table, you write what will be the output, where you will get a 1, where you will get a 0. Just define this part. Okay. So we will do this OR gate in Logism. So we will put this OR gate here. So for A, B, 0 plus 0, then we are getting a 0. If we add a 0 plus 1, then we will get a 1. If we add 1 plus 0, then also we will get a 1. And 1 plus 1, then also we will get a 1. So this is our uh, logical OR gate. Any doubt in logical OR?
No, ma'am.
So next is this NAND gate. So what is a NAND gate? It is a combination of AND gate followed by a NOT gate. Okay. So we are combining two gates, AND gate and NOT gate. So it is the complement of AND gate. So first we will we will use a AND gate, and then we will add a NOT gate. So whatever the output we are getting here, so it will just become the opposite of that. Okay. So here is the expression. So y equal to a and b, or a into b, and we are just complementing it. That's why we have put a dash on the top of it. Okay. So this is the Boolean expression for NAND gate. Okay. This is the symbol. So we have put a AND gate, and we have put a complement here. It means it is a NOT gate. So it becomes a NAND gate. So this is the Boolean symbol. So it will be same as AND gate, but we will put a bubble over here at the end, meaning that it is a AND gate and a NOT gate. And whatever the output of our AND gate was, like if we see the AND gate, what was the output? 0001. So it will just become the complement of it, means it will just become the opposite of it, because we have put a NOT gate. So it will become 1110. So that's why our output has become 1110. Okay. So if we have to define it here, so what we can say, we will get a output as logic 0 when all the inputs are 1. And if either case the inputs are 0, then we can get it as 1. Okay. So if all the inputs are 1, then only we will get a 0. And if any of the input is 0, then we will get output as 1. So this we can define as NAND gate. See here, it will only produce a logic 0 output when all the inputs are simultaneously at logic 1. Any other combination is 0, then it will produce a logic 1 output. Okay, so this is NAND gate. We will do NAND gate in this logism. And one more is, what is NAND gate? It is a combination of AND gate and a NOT gate. We will see that the two should be similar. Fine. So this both circuit should work in a similar manner. For 0 0 we are getting a 1. Okay. For 0 1, see here we are getting a 0, but because we are getting a 0, it is getting inverted and becoming a 1. Then if we give 1 0, then here we are getting a 0, but due to this NOT gate, it is getting inverted and it is giving a 1. And for 1 1, we are getting a 0. The output is 1, but because of this NOT gate, it is getting inverted to a 0. Okay. We will just see the expression for this NAND gate. So this is the truth table. For 0 0 we are getting a 1. For 1 0 we are getting a 1. For 0 1 we are getting a 1. For 1 0 we are getting a 1. And for input as 1 1 we are getting a 0. What is the expression? A naught plus B naught. Sorry, this is wrong. I think it is taking some other gates. So it will be A multiplied by B, A multiplied by B and whole bar. Okay. Actually, it is doing some De Morgan's theorem. This you don't have to study. That's why I'm not going into details. So actually, it is using the De Morgan's theorem. This EC people will study in next sem. So that is the expression it was showing there. So next is NOR gate. So it is OR gate followed by a NOT gate. So it is a complement of OR gate. So here we can say it is a combination of OR gate and NOT gate, and this is the expression. So for OR gate it is A plus B. So for NOR gate it will just become complement of this A plus B complement. So whatever output we are getting at OR gate, it will just that. So for OR gate, the output we are getting as 0 1 1 1, so it will become opposite of this, so it will become 1 0 0 0. So here for NOR gate it is becoming 1 0 0 0. So here we can say in the definition we can write NOR gate will only produce a output of 1 if all the inputs are 0, and any other cases where input is 1, in either case the output will be 0. So this we have defined. If it will produce a logic 1 outputs when all the inputs are simultaneously at logic 0, any other input combination has a logic 1, then it will produce a logic 0 in the output. Okay. So this is a symbol of NOR gate. So it has a OR gate and a bubble is there. It means it is a NOT gate, and this is the Boolean symbol. So this is an OR gate and a bubble means it is a NOT gate. So we will do this in Logisim. So we will replace this AND gate with an NOR gate. And this AND gate with the OR gate. So for 0 0 we are getting output of 1. For 0 0 if we give, so it means 0 plus 0 means output is 0, but this NOT gate is inverting it. Any other case, it will give output as 0. Any other combination for 0 0 only, it will give a output as 1. Any doubt in AND gate, OR gate, NOR gate? So why
No,
is
ma'am.
NAND and NOR
Um,
gate called as universal gates?
Because we can create any gate with by using those two universal gates.
Okay, good. So we can make any other gates using this NAND and NOR gate, but universal gate is not in the syllabus, so you don't have to study what is universal gate. Okay, so you have to study this, and one more gate is there, that is XOR gate. Okay, so this is the expression for XOR gate. It is y is equal to a um, a multiplication b complement and b into a complement. Okay, and this is the symbol for XOR gate. So there is an OR gate, and behind this at the input there is one more line is there. So this is XOR gate. Okay, so this is the Boolean symbol for XOR gate, and this is the output for XOR gate. If we are using this expression, then we will get this output. So we will see how we are getting. So inputs are A and B. So the combinations will be 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So what will be A complement? A complement will be opposite to this A. So it is 0, 0, 1, 1. So it will become 1, 1, 0, 0. And what is the complement of this B complement? It will become from 0, 1, 0, 1. It will become 1, 0, 1, 0. Okay. So what is the first term? It is A into B complement. So first term will be A into B complement. Okay. So if we multiply 0 and 1, A into B complement, what is A into B complement? 0 into 1. What is 0 into 1?
Zero.
And 0 into 0?
Zero.
Zero.
1 into 1?
One.
1.
1 into 0?
0.
Zero.
Okay. So this is the first part of our expression. Okay, we did the first part of expression. So we will do this second part of the expression, B into A bar. Okay. So B into this B, B into A bar. These we have to multiply. So 0 into 1, what will be the output?
Zero.
1 into 1,
One.
0 into 0,
Zero.
and 1 into 0.
Zero.
Okay, so this is the output for this A bar dot B or B into A bar. Okay, both will be same. So what is the third term? We have to OR gate with these two gate, means these two AND gates. So these two are AND gates, and then we have to OR these two. Okay, the output for this first part and second part, and we have to first 1 plus 2 we have to do the give it as output. So we will add these two terms. So what will be 0 plus 0?
Zero.
0 plus 1?
One.
1 plus 0?
One.
And 0 plus 0?
Zero.
Okay, so this is the output for XOR gate. It is 0, 1, 1, 0. So saying the output and input of this XOR gate, what can we say? How can we write this truth table? This truth table, how can we write? Like we are writing for AND gate and OR gate. How can we write?
Yeah, ma'am, you're asking the Boolean equation.
No, definition. Like seeing the truth table, like we are saying now for AND gate, it will only produce a 1 if all the inputs are 1. So how we will write the definition for, of XOR gate seeing this table, truth table?
It gives 0 when the inputs are same.
Good. So here we can say that when the inputs are same, only for two input OR gate, XOR gate. Okay, this is different for three input XOR gate. So just write two input XOR gate. If both the inputs are same, then we are getting output of 0. And if any one input is different, then we are getting an output of 1. Okay, so this you can write in XOR gate. If you are asked the definition, first write this expression for this XOR gate, write the symbol, write the truth table, and explain this truth table. Okay. Exclusive OR gates will produce a logic 1 output when either of the one of the inputs is logic 1 and the other is at logic 0. See, either one is 0 and one is 1, it is written there, or either one first is 1 and the second is 0. So this is written in the first statement. An exclusive OR gate produces a logic 0 output whenever both inputs are of at same logical state. That is when both are at logic 0 or both are at logic 1. Okay, so this is for this first and last case. So if both the inputs are same, then we are getting a logic 0, and if any one input is different, then we are getting a logic 1. This we will do it in logism. So this is XOR gate, and this is a combination I made through this expression. Okay, through this expression. So first is this A dot B bar, and so this is an AND gate, this is second AND gate, and both the outputs of these gates we have to OR this. Okay, so I have made a circuit out of this equation. Any doubt?
No, ma'am.
So this is the first AND gate. Okay, so first expression is A dot B bar. What is the first expression? A dot B bar. Okay, so first we will do this. So first we are taking A and what other input is B. So how we will put a B bar? We will put a NOT gate. So it is becoming B bar. Okay. And both are A into B bar. So this is our first AND gate. And so this is the first part of the equation. And what is second part? It is B into A bar or A bar into B. So here from here we are getting a B and we have to take a A bar. So from A we are adding a NOT gate and we are making it as A bar. So this is the output for this is A bar B or B into A bar. Okay. So here I cannot write bar. Okay. That's why I am using this NOT symbol. This is a NOT symbol which is same as this A bar. So what is here we have done this, here we have put a AND gate for this. So what here there is OR gate. We have to add both these cases. So output for this first case and output for this second case, we have to add it. So we are using a OR gate because instead of this plus. So if we do this OR gate, if we use this OR gate, then the output it will become A into B bar plus A bar into B. So this is the final expression for our XOR gate. So we will see what is the output for this XOR gate. If we do 0, 0, then we are getting a 0. If we give a 0, 1, then we will get a 1. If we give 1, 0, then we will get a 1. And for 1, 1, we will get a 0. Okay. So we will see how it is working. If we give 0, 1, then it will, if both are different, then we will get output as 1. So if we do 0, 1, we can say this gate is getting activated. Okay. And this is giving a 1. And because we have OR symbol, so 0 plus 1, it is giving a 0. See, from the truth table, if you can see, if we give 0, 1, then this part, second circuit is getting activated, and from there only we are getting a 1. Okay. And if we give 1, 0, this first circuit is getting activated, and from here we are getting a 1. So next we will give 1, 0. So we can say this circuit is working. Okay, this is giving a 1. That's why we are getting a 1 over here. So this first circuit is getting activated over here. And if we give 1, 1, then this both is becoming off. So both is becoming off. So if we use an OR gate also, then it is becoming 0. So this is a complete XOR gate, and if in smaller form we can say this is they make XOR gate like this in smaller form. So this is the big circuit. In smaller form they make it like this, an integrated circuit. So this is how we are making bigger circuits into smaller circuits. So this is a big circuit, and in the smaller form it is like this. Any doubt in XOR gate?
No, ma'am.
So this is one question in your book. Okay, this is from your book. I don't know whether it will come in exam or not. Show how an arrangement of basic logic gates and or not can produce the exclusive OR function. So this equation, we have simply made this circuit from this equation, whatever I did in the simulation part. So here with first AND gate, we are getting as A into B bar, and with second AND gate, we are getting B into A bar. So how we are getting A bar? We are using a NOT gate. We are connecting a NOT gate, and how we are getting a B bar? We are connecting a NOT gate over here in the input. So we are getting A into B bar and B into A bar. So because there is a plus sign, we are using this OR gate. Means plus means OR. So we are these two outputs are there. So we are giving an OR gate. So we will get the total expression for this OR gate. Okay. So this might come in exam for exclusive OR. I don't know whether it will come or not. I think from this part only the definitions will come. What is logic gate? What is buffer, not, and or not, ex, nor, NAND, and XOR. That will come definitions. Any doubt in this?
No, ma'am.
Understood now how the circuit is coming?
Yes, ma'am.
Yes,
Okay.
ma'am.
So this is also the last class, so I won't teach any further. You can write your roll numbers and leave. Okay. And anyone has a network problem, they should say it within the class. Give a WhatsApp message within the class. After the class, I won't give you attendance. Some of the students are saying after 1 hour that give me attendance. That is not correct. If anyone has a network problem, you message it to me now before the class ends. So you can write your roll numbers and you can leave.
Thank you, ma'am.
I am also
Thank you,
posting
ma'am.
all the video lectures. Okay, if you are having some doubts, see the video lectures. I have put it in the classroom. So this will be processed in 1 or 2 hours. I will update the video lectures also.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you.